We'll begin this morning's program with a lecture from Professor Wendelin Werner. Professor Werner was a field medalist in 2006. His work is driven by curiosity to unravel the abstract ideas of the world around us. He's currently a Roosevelt Professor of Mathematics and Royal Society Research Professor at the University of Cambridge. He held professorships at Paris Sud University from 1997 to 2013, and at ETH Zurich from 2013 to 2023. At the end of the lecture, there will be a Q&A session moderated by Assistant Professor Lee Tian Xiao from National University of Singapore. Professor Werner, please.
Thank you very much. It's always a great pleasure and sort of simultaneously a big responsibility when one has to, address a broad range of clever young minds. We try to stimulate your imagination in some ways, not to give advices or things that are not valid anymore or wouldn't be working well. On the other hand, the good thing is I know you're all very clever and you're able to, whatever we say, which you feel is wrong, you just discard it and say, okay, this old guy just doesn't really know about what I want to do, and I'll do it my way, and that's the way it should be. The other thing is, I'm sort of the mathematician around, like of course, some other speakers are, in computer science or some mathematician disguised as other scientists. But still, there's always, in this general audience type talks or conferences with, more than one topic, there's people say, okay, now comes the math talk. Let's see how much we get out of it. The bar is usually quite low, so which helps us to jump above it because the expectations are not necessarily very high. Anyway, so what I want to try to explain you in these next 30 minutes is sort of a few snapshots that are sort of disconnected, but you can connect them together if you'd like, about what type of things I like to think about, why, and what sort of objects I like to think about. One general rule is that in each science, and that's valid as well for mathematics, there's a huge variety of topics and ways to address them. And so, in some sense, they're completely, within mathematics, there's an array of completely different type of, subfields. And the type of ideas, the way you approach them, is actually quite different from one part to another. So what I'm going to talk to you about is about random structures, random objects. And what motivates me somehow deep inside, despite everything I'm going to tell you coming from physics, is the objects themselves. So it's just the idea of these objects and how they could be incarnated in some real world around us is nice. Now, maybe I should start with one little couple of life stories about my, when we went to school. And I always remember maybe the first time where I was actually exposed to the fact that this mathematical world existed was at primary school. I had this wonderful teacher who was able sort of to make sense of what the math curriculum was for primary school students in Paris, in France at the time. And so we were learning about something, a sort of elementary set theory, which now is sort of more the type of things people in computer science do. But at the time, it was like for 8-year-old kids. So the idea that you had a set, which they represented as a potato here. Oh, yeah, by the way, I choose deliberately always to not have a PowerPoint presentation in the usual way, because I always feel that it's sort of not suited to math in the right way. When we are watching something, we are more passive. We're not creating it in our heads. And so I try just to scribble things and to let your brains maybe work a bit more than having the full sentences there and just reading them in a passive way. So the idea was, this story, I don't want to lose too much time with that, but basically you have two sets, right? One set with dots and one set with crosses. And then you define what they call the map from one to the other, which is just a way to assign to each point on the left something on the other side. Okay? And then we were told, well, there's this thing, we say this is an injection if every point on, any two different points on the left are mapped to two different points on the right. So in other words, every point on the right has at least 1 or 0 arrows incoming. And so then you're a small kid, you say, well, okay, this just means that, if there's an injection, there are more, there are less crosses than dots. And then you have this other thing, which is a surjection, which says, there's a surjection if every point on the right has an incoming arrow. And then you say, well, this means that there are at least as many, then there are more crosses than dots. And then you say, well, then that means that the two sets are essentially the same. If you have both an injection and a surjection, they have the same number of elements, and they're essentially the same, except that you can change the name of one cross into a dot, and that you call it bijection. And then I very much remember that I raised my hand. I said, yeah, thank you very much, but what happens if you have infinitely many dots or crosses? Is it true that if you have an injection and a surjection, then the sets are the same in the sense that you have a translation of the names of the one into the other? And the great thing was this primary school teacher said, oh, I don't know. I look it up. That was in the mid-70s, so she went back home, looked at Encyclopedia Universalis, and came back the next day and said, yes, it's true. Some people have shown it's true, but it's too complicated for me to understand why, the proof. And you'll have to learn much more, and maybe later when you're grown up, you'll be able to read it and to understand that it's true. And then, I felt, that was like the best teacher ever, right? First of all, saying, I don't know, which is, the second thing is, there's a whole world out there, and, very simple question has an answer which, might be very elaborate. And so then I sort of started feeling that, okay, now I have to do fingerprint. There's a whole world of mathematics, abstract mathematics out there. Maybe I'd like to be able to understand that proof later on. Then, a bit later, in okay, so how should I do here? Came, the thing where we learn about the rules of physics in high school. So the first rule of physics I learned was, that was very strange, but electricity. So electric circuits, and we had no idea about electrons or anything, or so. And then we had to do pictures like this with abstract circuits, and somehow the understanding what was going on in there. And I very, very, very remember that the teacher said, yeah, and then you close the switch, and then the electrons start marching, go along the circuit in this way to go from one pole of the battery to the other, and that's the way it works. And you can compute and have formulas to try to understand the current and these type of things. And then I again raised my hand and said, yeah, sorry, so it means that if you put on the switch on your thing, then the electrons somehow that are sitting somewhere in the middle of your circuit wake up and say, oh, now I have to march, this way. How does that work? That can't be true. There's no telepathy telling you that the electrons have, suddenly decide to behave this way or that way. And that teacher wasn't so great because when I asked, how does it work? How do electrons decide to do what they want to do? What they are actually doing? She said, no, that's not what I'm teaching you. I'm just teaching you how the rule is and just how to apply it. And don't ask these stupid questions. All right, so, and then came, of course, more importantly, then you learn about Newton's law, electromagnetism, magnetism, and things. And again, I just couldn't understand how it worked, right? So I, again, raised my hand, said, sorry, that's great, but the Earth doesn't think, it's not measuring the distance to the sun. How does it know it has to turn left, in order to, because it measures the mass of the Earth, how something has to, travel between some information has to go, and there should be automatic, way of, things going back and forth. And again, high school teachers in physics were fantastic. But at the very end of the day, I was always saying, no, that's not, please, explain me more and more. And then at the end, he said, maybe you're not going to be, maybe physics is not for you. If you stop, it's a bit like, you get the thing about yesterday morning's lecture about NO and you say, well, wait a minute, what is N? Well, you're not going to get that far, if you stop, immediately. So you have to, at some point, accept something. And, but still, this has sort of, pursued me somehow through the whole, curriculum, these type of questioning. And each time I was recognizing in the math curriculum structures and ideas that were relevant to what happened, to these original questions, then made me feel very, very happy. And I loved these math objects that were around. So, for instance, you learn, and this is a type of thing that it's very surprising when you ask math students after a bachelor saying, okay, tell me, what is the nice harmonic function in space? That actually many students wouldn't really know. So, you learn this one thing or you don't learn, but you should, is that imagine you have a sphere. Now I'm in three dimensions, right? I have a sphere here, and I have a point here. So to each point here, you can associate the distance to the origin. So we call it d of 0x. That's the distance between x and 0. Now, if you have the distance, you can look at the inverse distance, 1 over the distance. Now, there's a magic property of 1 over the distance to the origin. And this magic property is if you average the value of 1 over the distance to the origin on the sphere here, you get exactly 1 over the distance of the center of the sphere to the origin, right? So this function, 1 over the distance to the origin, is what we call a harmonic function. It has the property that the value at a point is the same as the average value on a sphere around it. Right. And then, you see that and you say, aha, okay, I know 1 over r, that's the Newton potential. Now I start getting some information about, why I was told that in the rules of things you can replace something with the center of mass when you apply these rules. And this has to do with these, structure of harmonic functions. And that's good. And of course, I'm not inventing physics here. Of course, every physicist will say, of course, the potential, something preservation of energy, or there are lots of ideas that tells you, of course, that's sort of elementary things, but that's always comes somehow in the way things happened historically, and therefore ended up being implemented in the curriculum is that the physicists somehow invented intuitively some math ideas that were ironed out maybe or deeply understood mathematically a bit later. And then, yeah, so basically all these harmonic function things, Newton didn't know about harmonic function. He had just this one over R potential ideas. All right, so now another related cousin to harmonic functions when you study probability is Brownian motion. And Brownian motion is the reason why I chose to go into research in mathematics, in probability theory, and so on, because when I saw this object, I said, that's my friend, I like it. I like to think about it. It makes me smile, and maybe it's a good idea to have, do it, smile all my life by thinking about these type of nice objects. If I can get paid for that, that's even better as a mathematician. So Brownian motion is just this random trajectory. You should imagine just a trajectory of a random fly without brain. Of course, we know flies don't, they don't. So at each instance, somehow it chooses a direction uniformly at random, and it changes its mind all the time, and therefore it sort of wanders around like that. And it's a very, it's a very strange mathematical object because the trajectory you define is actually, a very unusual type of trajectory. It's continuous, it moves about continuously, but because somehow it changes directions all the time, it's very disorganized, and therefore it ends up, the trajectory, if you try to draw it with a real pen, not a pen like that, you run out of ink instantaneously because actually the length of the trajectory is infinite, right? So it's, it's a very fractal type curve, which somehow, it has infinite speed if you want. You have this infinite energy in the trajectory that moves around, and therefore, it's actually not that easy mathematically to show that it is a continuous trajectory. So you have this object here, and the nice thing about Brownian motion, and one of the nice things, is that it is isotropic, right? It just doesn't, all directions, are the same. Somehow it tries to move completely erratically. And so, therefore, there's a deep relation between harmonic functions, which have to do with averaging out over all directions, and this isotropy of Brownian motion that you can, make rigorous. And then you can relate all the possible harmonic functions to something having to do with Brownian motion. And there you realize, and you have to, this is just like, for mathematicians who study Brownian motion in some sense, who say, well, okay, now a posteriori understand what's going on in an electric circuit. It made me very happy. And of course, that's not new. People in the 50s, worked that out. But then say, well, actually, the electrons, any electron in an electric circuit doesn't feel anything. It just performs Brownian motion in the electric circuit. That's what the electrons are doing. The only thing that happens, right, is that if you have a battery, right, on one side of the battery, electrons are thrown into the system, and then they move around like Brownian motion in your electric circuit. And then at some point, when they reach the other side, they're gobbled up and drop on the other side. Okay, and then the whole thing about resistance and all that can be reinterpreted in terms of, say, okay, how much time does it take for the Brownian motion to find the other side when it starts on one side? And you can recover all these rules that were around, for Ion, and then you say, okay, that's the way it works, right? Sort of that's these electrons, and you can interpret, all these notions about resistance, conductance, and so on, in terms of just these random objects. And now you say, then I said, now I understand. I thought, okay, now I finally understood what I was told when I was 12 years old. I have this intuition. Of course, you might say, well, what are you talking about? You think you understand, is Brownian motion more real, or, is it closer to the reality, or okay, well, in my impression, yes, because I feel, this is really what the particles are doing. Now, what I want sort of to explain now in the remaining time is this idea of, for the much more complex physical theories, you have understood, yesterday the standard models was mentioned, and you have all these, different type of particles that you can read in on textbooks or on Wikipedia, gluons and bosons and fermions and electrically charged things, where physicists have, invented lots of very elaborate mathematical tools and theories that, were supposed to describe these particles, predict certain things, and then able to make experiments that, was confirming that. And one big success story was the story of conformal field theory, where basically you had this one fairly abstract theory that was, at the end of the day, describing things having to do with phase transitions in 2 dimensions. So maybe when you'll hear Duncan Haldane's talk, you'll see a bit of a glimpse of things related to that with the quantum Hall effect. So what I have in mind here is that, okay, maybe I should show you that one here first. You have some sort of system, right, where, you can imagine this of, melting ice, at the phase transition where, black might be ice and white might be water, or, something like that. And, at each point you could be either of them. So this picture is called percolation, where you just toss a coin with probability 50%. Each cell is white and each cell is black. But then you are sort of interested in the shapes that show up there, and you have this idea that if you have like a big island that sort of collapses or melts down, that then you have sort of lakes forming in the island that start being big, and inside the lakes you still have islands, and inside the islands you have lakes. So we're looking at a picture more like that, which is a picture you can't see anymore because then it's just gray at first glance. But in this gray stuff, you have still structures of large islands type things. So at the beginning, somehow, the question coming from what is called statistical physics would be to say, well, you have these structures. What can you say about these large-scale geometric structures? What physicists have invented is what they call a field theory, which is sort of, again, some way, slightly, much more elaborate, of course, and to describe interaction at distance, where you say, how could you correlate, I observe something here, observe something there. How do they interact? Are they in the same island or not? And how can you, make sense or describe these things? And so to make a long story short, I just want to emphasize one small thing, which is that one of the key tools in this conformal field theory, and in the mathematical tools that we then developed later, is this basic, old, beautiful mathematical structure, a concept developed by Riemann, but of course Riemann's proof was wrong, and actually it was proved by somebody called Osgood for the first time later. But of course, Riemann had the main insights, nevertheless. It's so-called Riemann's mapping theorem, which just says that if I have, 2 dimensions is nice and flexible in the sense that if you give you any 2 shapes, so here a square and another one, there's a way to deform your square into any other shape you want in a way that preserves the angles everywhere. So you see here I have the square on the left, and you sort of see how with the colors, you fold it, in a certain way, and you see that, the things on the left were, when they cross doing a square, 90 degrees angle. Is still true on the other side. So this idea that you can deform 2-dimensional space in an angle-preserving way, which is related to complex numbers and, number of theories if you learn about mathematics. This is, one essential tool and one very important deep theorem behind all these field theories, because the idea is somehow that if you, do the same picture with this thing here, you distort it in an angle-preserving way, the global, connectivity structure should be in the rules that govern that should be preserved. So to make a long story short, what we tried to do, and then it worked out to a good extent, was basically to say, well, okay, you have these theories that describe these long-distance interactions and where you make you able to predict, features of these phase transitions. So, for instance, there's the famous question about a ferromagnet. If you have a magnetized piece of iron, you heat it up, and when it reaches this sort of Curie temperature, then suddenly the magnetization drops. That's another type of phase transition. And what happened exactly at that point? How does that function? That's exactly these type of questions that are behind this type of physics. Now, we'll be able to say, well, we know how. I have a constructive way to construct these actual random pictures, not just the correlation functions, but behind these correlation functions, there's actually a random object, a random structure that you can describe, and then you can look at it. It can make nice pictures, but and so on. Somehow, you should view this picture here as this black stuff would be, at the moment when your island collapses and the lakes become big inside, that would still be the set of points connected to the boundary of the island that are still connected before the moment where just after that, when it melts a bit more, everything will become disconnected and collapse. And this is the type of random structures one has to look for. Now, the nice thing about that is that okay, that's the picture I want now. The way we construct them involves Brownian motion again in a very surprising way, because Brownian motion is something that doesn't interact with, it's just moving around, doesn't have any brain, it doesn't know, where to go. And so what's sort of emerging now on the math side is this idea that actually, things are maybe simpler than we thought. Is basically that there is a structure which is just, here is what is called a Brownian loop, right? It's a Brownian trajectory that is closed. And you can think of that as some canonical way in which space, in any space, you can form, like shortcuts, little cracks appearing here or there. And these cracks will, have shapes of Brownian loops. So you have Brownian loops that appear independently, completely at random. And they can intersect. And of course, if two cracks intersect, then they become the crack becomes bigger, right? Sort of it becomes larger. So somehow you let it rain these Brownian cracks for a given time, c. I call it c because that, in the end, turns out to be what physicists call central charge. So you let it rain at a time c. And you look at the, how the cracks look like. This union of loops. And it turns out that all these fractal structures, these strange domains I showed you before, there's one simple way to describe them, which just saying, you take the union of all these loops, and then you take their outer boundaries. They form islands. Like that. If these islands haven't merged together, all together into one giant structure, then you can look at the complement of the islands, so the set of points that haven't been visited by any loops, and that you can sort of still connect to each other. And you say, well, these are these fractal sets of the type that I was trying to describe here. Right? So you should view here all these holes here are clusters of loops, and the black stuff is what is sort of remains connected in the complement. Now, important feature is that in these, collection of loops here, everywhere, you have infinitely many very, very small loops. So these clusters of loops are very complicated because you have one big loop, smaller loops attached to the big loop, smaller and smaller loops. So it has this dendritic type feature of lots of loops being attached to each other. Now, there's one specific collection of loops that has a very, very particular property. And that's the collection of loops which has sort of a magic property that if you erase the colors of the loops, then all the loops here are not green or white, but they're all white. Then, somehow the way this cluster is subdivided, was created into loops, is something which is, you can obtain by independent, so in some sense, if I have a white loop and a green loop that overlap, you wouldn't know, was it two loops, one loop? Do you do a figure eight or just two loops? And the answer is, well, you toss a coin to decide everywhere. So that in some sense, these loops are indistinguishable. And then you say, oh, wait a minute, I learned that from physics. Bosons, there are certain particles that have a feature that they're undistinguishable. So this is related to that. And then you say, well, actually, this collection of loops, we learn, this is going to be related to this called the Gaussian free field, which is related to what physicists call, this is the bosonic free field, which is somehow the most uninteresting physical model in some sense. This is the one where nothing happens in the vacuum or something. But then you realize, oh, wait a minute. So if I take this one, where these, you could do that in 3 dimensions as well. So in 3 dimensions, you can compute this fractal dimension of this, now it's not an island of loops. It's sort of, like a giant blob of, curves, attached to each other. So you can compute what is called the fractal dimension, so how thick it is. So you can compute that this fractal dimension of this blob of loops is 2.5. So you can do maths, with it. So it's a pretty thick thing. And then you realize, wait a minute, that's random object is probably what might be behind the scene when you talk about gravity. Because how does the information flow from the sun to, the Earth? And now I'm not a physicist, right? I'm just like a crazy mathematician who likes to invent things and be happy in his corner, right? Or his or her corner, because we are like, But what you realize that these collection of loops, they might be actually, the things that physicists, when they say propagator, this is the thing that transmits forces and so on and so on. That's how, something between me and the Earth, that pulls me down has to do with the fact that there are, like some chain of loops of dimension 2.5 that are connecting me there to all the gravity things, and that pull things together. So of course that was like a crazy statement, but it's just to say that 30 minutes talks, you have to be a bit populist and just try to, it's more to stimulate your imagination than to convey a rigorous statement here. This idea that actually, you have very natural mathematical objects, this collection of loops that are connected to each other, that have, interchangeability properties and so on, and that these things, at the end of the day, might actually not be unrelated to these basic questions that, have, been appearing in your mind at some point before. So. And indeed, the motivation why I am attracted to these type of things, why we came up with constructing these clusters of loops and doing like that, and all physicists in the 70s have, that was a very sort of popular topic, these sort of random walk representation of lattice models and things like that, big names to be mentioned there. So why people were attracted by these particular random structures to describe something that looks like, deterministic world around us, that's a very useful and stimulating thing. Okay, so I going to conclude now. Just hope that was entertaining enough. I hope you agreed that not having, like a PowerPoint, I always feel like, when I used to like seeing the handwriting of mathematicians on blackboards, and I always feel you could see some aspect of their personality. It was sort of more human than, these PowerPoint presentations. So I hope you didn't miss any, more pictures or more something that was this sort of blackboard talk. Okay, so thank you very much.
Thank you, Professor Werner. May we invite you to remain on stage as we invite Professor Lee.
So thank you very much, Professor Werner, for the wonderful talk that took us through a journey of your own motivation to become a mathematician and also the very interesting connections of different areas of math and physics. So now we'll open the floor to questions. So please, if you have a question, please go to the microphone and ask away. So while we're waiting for the questions, I will jumpstart with some questions of my own. So you showed this very nice, interesting picture of this random walks on the sort of on plane. And there's very interesting interactions with these loops forming, more complex structures. We know that this magnet is three-dimensional in real life, and I'm sure there's also a three-dimensional analog to many of these questions. And can you comment on whether those are much more complicated or interesting?
No, I mean, so what I said at the end, there's a two-dimensional world. I mean, very often it happens that, you want to understand one specific thing, which has to do with these, in that case, this conformal field theory, which is two-dimensional. And then you realize that something is behind the scene, that you can construct things with a three-dimensional, with these Brownian motions, these collection of loops. And then, but the relation between the loops and these fields, Gaussian free field and harmonic functions and so on, works in any dimension. So you could do the same in 3 dimensions. And so it's, some aspects of what happens in 2 dimensions you cannot, build further, but something can go in any dimensions, and actually going in dimension 4, 5 is actually even more sort of interesting. But, and it sort of raises, a number of natural questions that do not seem completely unrelated to some other aspects of physics that I was always, had problems with. Yeah. Yeah, so that's sort of, so this 2.5 dimension things is a 3-dimensional story.
Right.
I mean, one other question, I mean, just to explain that, mathematicians can be sometimes, like the children, you have your children, the ones who always ask, why? And then you give the answer, but why? And then why? I said, okay, stop that. I liked to, I remember, you learn about the bit dimensions and things like that, and then you say, okay, why do we live in 3 dimensions, right? So, and then you say, well, you have all this thing about harmonic functions and properties of Brownian motion and different, if you have a Brownian particle in 2 dimensions, it moves around, but it will always come back near its starting point. It doesn't go away to infinity. That's not good, right? Because, you want, stuff to go away, disappear, so, energy has to dissipate in some way. So life in 2 dimensions wouldn't work, or energy or something. And in 3 dimensions, the nice thing is, the Brownian motions go away to infinity. So you can define this loop structure directly in the whole 3-dimensional space. You don't have too many big loops. You are not bothered by big loops, coming here. They are not there. Wherever you are, you see only, not too many big ones. And then Brownian motion has this strange property in 3 dimensions that if you are, it has double points. So it has points where it intersects itself, which normally, if you have a 1-dimensional trajectory, you take 2 lines would typically, chosen at random, will not intersect each other. They would have to, be very, very lucky to happen to be in the same plane. But Brownian motion are a bit more erratic, a bit thicker somehow than straight lines, and therefore when you take two independent Brownian motion, they will actually intersect. So these chain of loops will exist in 3 dimensions because you have these 2 different loops will actually hook up, right? So anyway, so all this to say that you can cook up some weird rational things, and 3 dimensions only one, only possible one for rules of physics to some rules of that sum to actually work, and therefore it's we have to live in 3 dimensions. That's how life was created, or the world was created in 3 dimensions, because that's the only way it works. So you can always do your little things, and of course you say that this is very much in this interdisciplinary question from yesterday, that you come up with that, and this is like from a physics perspective, this is like babies playing, but still we are quite I don't mind. We are happy to do that.
Yeah, of course. Right, thank you for the answer. So I think we have a question here from the audience.
Hi, thank you very much. This is the first time I see a math talk, and that was that set the threshold pretty high, so that was very nice. I have 2 hopefully small questions. First one is that I have used Brownian monsters for animations, for science, and moving cells and stuff. So that would be very nice if it's easy to translate those closed Brownian monsters into equations or a program. So I want to know how easy that is, because
that's very easy. That's very easy. I mean, basically, you mean the loops?
Yeah.
Yeah, I mean, to create a Brownian loop, basically, you just take a normal Brownian motion of a certain time length, so it ends up there. And then you just subtract the sort of linear interpolation from between those 2 points. So you pull this one back, and the distance sort of, so it's just like Brownian motion minus a linear term. And so that's very easy to simulate.
Perfect. And the other one is, you mentioned the dimensions of these fractals and stuff.
Yeah.
I know that for other fractals, you can calculate the actual dimension. And how easy that is to calculate, and is it kind of like, for example, for the 2-dimension like Brownian motions, if it's that constant, or if it changes randomly depending on...
No, what happens with all these fractal things that have some physical meaning or consistency is like you have this long fractal thing. The fractal dimension is measuring something which has to do with the average behavior of your curve, and therefore the dimension of a Brownian motion or the dimension of these clusters will always be the same. It's just whatever Brownian motion you look at, it will always, with probability 100%, have that type of fractal dimension. To prove that the dimension of these clusters of loops is 2.5 in 3 dimensions, that's a very hard thing, because you have to go through a number of things, and actually the proof is not completely written up yet. So this is just like a Brownian motion itself is something is easy to understand, to compute it. I mean, easy. Okay. If you study 5 years of math, then you can make it. But that's something that's sort of in textbooks. But then, for more complex random structures to, I mean, that's another thing, is that, there are two things. The first thing is they have a given dimension that will be always the same once you decide the rule of how to construct them. In some sense, getting a formula for the actual dimension is not something we are particularly interested in. It's just there, you can compute it or not, but this is typically the type of thing that is very relevant when you want to, convert it on the physics side, because these exponents, these numbers correspond to exponents corresponding to things you can actually measure in actual experiments in case it relates to real world type things. So the fractal dimension of these islands of magnets at the critical point will be related to something that people studying ferromagnets in the 19th century or a bit or later, early 20th century, they would have seen this particular exponent popping up in the magnetism near the critical point for iron. Yeah.
Perfect. Thank you. I have a question over here.
Yes, thank you for a very interesting talk. So you started describing your interest in these mathematical objects. I'm interested in how you find its connection to physics, such as phase transition.
You mean how
How do you move from mathematics to find
Well, I
this
mean,
connection?
the way it goes is really like, there is this whole area which is both on the math side and on the physics side. You could call it mathematical physics. There's journals of mathematical physics and a whole community of mathematical physicists, an international association of mathematical physics. So, there's a sort of a borderline there of people talking to each other. And on the physics side, people, try to come up with formalism and mathematical objects that allow them to maybe, put some of their intuitions into the reality there. And I mean, there have been a number of Nobel Prizes, in physics for exactly that type of, ideas. And then on the math side, people say, wait a minute, some of what you're saying there, we don't understand or we don't accept. We want to have our way of trying to make sense of it. Many times, at the end of the day, you say, okay, it feels like, putting the dots on the I of what the physicists had said, namely, their argument was directly rigorizable somehow. But sometimes, there were some actual missing things. So there's these random geometric structures, the fact that you had, way to put your hands on it. That is something that is actually not, in the culture of, probably because of the way things have been, are taught or how you learn to accept, these things that, interaction at distance functions that way, and that been maybe not so prominent. The other thing is also that, that's just my interpretation. I think physicists might disagree or agree, but that there's always this idea of coming from the quantum world, which I haven't talked about here at all, that, there's a formalism, it works. And then you look at the videos of Feynman, and he tells you, don't even try to understand it, right? It just, this is the way, and here we're talking with something, what I talked to you is sort of Euclideanized, back to the Euclidean world of ideas that came back from this quantum world. And in that case, you can actually, still have hope to actually understand it directly. So that's sort of, I mean, how far this goes, I don't know, will lead to, what probabilists are now, playing around with. There's this, one of the most amazing probabilists was a guy called Harry Keston. He had his webpage at the University of Cornell. He said he liked to dabble in, little toy models from physics, and he did all these amazing things. And he's among those people, the prizes, like Nobel Prizes. So there's one thing very often you have to do in order to get it, is to be alive long enough, right? If you're unlucky and you die early, there are a number of fantastic people that just, the way some of these prizes are given to people of a certain age or have to wait and then just doesn't. So he's like, god of probability. But he would say, I'm just playing around with little models. I'm not, pretending to be. Of course, in his physics department, Cornell, you had like Fisher and top physicists there. So he said, just. But still, I have a strong belief that there's still something we can say from this probabilistic perspective, and especially the part of probability theory which has to do with continuum structures. Here we're really playing with these very, very, intrinsically continuous ideas that don't work really in the discrete. And if you think about the history of Brownian motion that I mentioned, basically people would say, who invented Brownian motion? Okay, it's not Brown, because he was just looking at little particles. And then, in the literature say, well, it's actually Einstein. Right? So he computed the Avogadro number using ideas having to do with Brownian motion. And you ask physicists, what is Brownian motion? They would say, it's random walk with infinitesimal steps. It's random walk. So, this idea that it is actually a discrete model. And many of the ideas that are around on the physics side are things where you think like Feynman integrals or things like that. You think guided by the discrete world, and you say, well, I treat the continuous world if it was the same as integrals and sums, it's just the same. And here you have some subtle things going on in this mixture of continuum and randomness that might be interesting to you. Okay.
Okay, so thank you for the answer. So I think in view of time, let's conclude this discussion session. I'm sure there's more chances to interact with Professor Werner. So thank you very much, Professor Werner, for the wonderful talk.